Hello, everyone. My name is Dogus Cubuk. I'm a co-CEO and co-founder of Periodic Labs. And we combine simulations, experiments, and LLMs try to accelerate physical R&D. So for the next few minutes, I want to talk about whether AGI, either today's AI capability or the future AI capability, could just zero-shot the next big scientific breakthrough. And I say it has to be zero-shot because the breakthrough, by definition, can't be in the training set. So it must be something that's different than what's been done before, so it has to be done without previous demonstration for that breakthrough. You know, another way of thinking about this is, can thinkism ever be enough for advancing physics? So thinkism is this idea that you lock yourself in a room and you have all the textbooks, all the previous experiments, papers, patents ever been done in the field. And then if you think really hard, whether you're a human or AGI or AI, a bunch of agents, can you advance physics? And I will argue for the next few minutes the answer is no. Because the universe is too complex for any intelligence, whether it's humans or machines, to think their way into the scientific advance. So what's the alternative? The alternative is what we've done for centuries, which is you iterate with the universe. You have a hypothesis, you try it. It usually doesn't work on the first one, but you learn from your failure, and then you keep trying. So one very interesting history to the study for this topic is the history of superconductivity. You know, if you study history of superconductivity, you learn a lot about humans, science, scientists, academic publishing, archive, etc. But today, I'll just focus on a few things. So the superconductivity for the first time was discovered back in 1911, and it was not discovered because an incredible human just thought really hard and then said, okay, if you take mercury and figure out how to lower the temperature, electrons will feel an attractive force through phonons. No, what happened is Ahnes's lab, this lab led by Kamerlingh Ahnes, for the first time created a capability that can lower the temperature below any temperature recorded before, and it was around 4 Kelvin. They got it down to 1.8, but turns out for some metal like mercury, if you can get it to 4 Kelvin, it will superconduct. So it was actually a side project of the main effort, which was to liquefy helium. And a few years later, Ahnes got a Nobel Prize. But very important to note, Nobel Prize was not given to superconductor discovery. It was given to the fact that he could liquefy helium. And if you look at the rest of the history, it's full of examples like this, where the big innovation wasn't done fully intentionally, and it wasn't done by thinking really hard, but it was done by trying a bunch of things and iterating intelligently with the universe. So another really good example is around 1958, John Bardeen and collaborators figured out the theory of BCS superconductivity. So this is conventional superconductivity, and it's great, right? Now the humans understand how superconductivity works. We can use that understanding to discover lots of other superconductors. But that's not really what happened. So if you follow this curve from 1958 to around 2000, there's been really major advances into conventional superconductivity. The biggest one, the SODA in deep learning language, is magnesium diboride, MgB2. But if you look at how that was discovered, it was not discovered by humans taking the theory, thinking really hard, and making the material. It was more like they were trying tens of thousands of materials, and that particular one happened to be a really good BCS superconductor. And of course, the other really good example is the cuprates. Around 1986, Alex Mueller and collaborator were able to find the first high-temperature superconductor, the unconventional one. But if you look at his Nobel Prize speech, you realize he was actually trying to find a conventional superconductor, because he didn't even know what an unconventional superconductor would be. So this is just for superconductors, but if you look at other aspects of material science, chemistry, solid-state physics, so I'm not talking about math and theoretical computer science. I think that's a different regime. But if you look at complex systems like physics, chemistry, material science, you realize that most things were found by either accident or a bunch of trial and error. Okay, so if this is the case, what does this mean for agents and LLMs? So I think we're fine. We just have to figure out how to use agents in the scientific method that we've been using for hundreds of years. So a very simple way of looking at it, right? We have some observations, we come up with an hypothesis, we try the hypothesis through an experiment, and then we look at the result. It will probably not work very well in the first time, but we understand why it failed and we try again. So this is the typical scientific method, but how we can improve this with LLMs and agents and machine learning is we can insert it in a bunch of places. So one example I can give is the simulation part in the very middle. So the simulations are already completely revolutionized by machine learning. So today we use force fields which approximate quantum mechanics of the ground state. And I can't, even if there's another AI winter, I can't imagine ever not using machine learning anymore for force fields. Another example is, of course, AlphaFold. Now we figured out how to do protein folding way better than before, thanks to machine learning. But force fields, AlphaFold, these are all tools, right? They don't actually give us the next big drug or the next big superconductor, but they're very useful tools. And there are other tools, of course, such as characterization, which helps us look at the experimental data and figure out what happened. It's very technical, but AI can really automate and scale that up. And at Berkeley here, there's been some frontier work showing how you can use robotic arms to try a bunch of things in the lab for synthesizing powders, and characterization is the obvious thing you can improve with AI. Another example is literature search, going through all the papers and figuring out what other ideas to try. And of course, DOE, design of experiment, where based on all the experiments you've seen so far, what should be the next experiment? So in our company and outside our company, AI is making a huge impact on all of these parts. And of course, it's not this clean. It's actually much more complicated. It's a spaghetti plot where everything interacts with each other. But you can easily see how the whole scientific method can accelerate if we put AI in it intentionally and carefully. So my last slide here, I just want to say, in my opinion and in our company's opinion, this universe is too complex for thinkism alone to innovate. So instead of looking at the current LLM progress and getting discouraged, especially if you're a science student, you should think the opposite. It's actually a really exciting time to do science. And what I would recommend is to fully focus on understanding the fundamentals. If you're a physicist, study the theory of superconductivity, study solid-state chemistry. If you're a biologist, study what's important in biology, I don't know. And really understand the scientific fundamentals, experimentation, because you realize that a lot of progress happened when people came up with new experimental methods, new techniques, new measurement tools, and you can contribute to all of these. And as you create new experimentation methods, new tools, then AI will benefit from it, because AI will see more data and it'll be able to use its thinkism skill to make sense out of it faster, in bigger scale, and then hopefully the next experiment you try is more successful and more intelligent. Thank you.